Welcome back. This is class number 7. And as described in the last video, this is a ridiculously easy example that I think is it's worth going over, looking at it, and I'm going to try to belabor it a little bit to help you organize how you approach this topic. All right, so we have a piston, and this is the topic is energy in the first law. The piston cylinder, a piston cylinder compresses a gas with a piston work input of 200 kilojoules. Since the mass becomes warm, it loses 45 kilojoules by heat transfer to the piston cylinder walls. Consider the gas as a control volume and determine its change in internal energy. Like I said, this could be done in just one equation, but we're gonna just think about it methodically. All right, so I'm going to draw out, I drew it differently on my page, but we're going to have a little piston right here, and it's going to go down, and here's going to be our control volume within here of the gas, moving down right here. So it's going to move down, and in the process of moving down, it has added work into this system. Now, because this is not insulated, I'll draw it like here's a cross section so we can see maybe it's aluminum or something. We have heat dissipating from this, right? So this would get kind of hot because work would put in there, but then heat would start to release outward. So I'm just going to draw one of these with an arrowhead, and we'd have this out. All right, so here is kind of different from what we had previously with our control volume, and sort of making that point, right? So we had heat coming in and we had work coming out. So our sign conventions are going to be maintained and opposite. So the work in was equal to 200 kilojoules, and the heat out is 45 kilojoules. If I went to the big equation that I have right here, which is, I'm not going to, well, maybe I'll put it here. We have that E 2 to E minus 1. We usually just ignore that guy right there. We just look at this right here. We have what happens to the internal energy plus 1/2 m V2 squared minus V1 squared. Am I going to have enough room over here? Let me kind of squish this in. Mg is Z2 minus Z1, right? Because we're moving from point 1 to 2. So then when we were looking at this effect, we're going to subtract 1 from 2. It's going to be equal to Q1 to 2 minus W1 to 2, right? So we're moving to the states. Well, we can, let's say that the potential energy was not enough to matter. And we can assume that the kinetic energy, that it started from rest, it moved, and then it stops from rest, right? So there's really no change. This thing happened between these two states. We're not assuming that dynamics is involved. So all we really have is what has happened to the internal energy. Well, the internal energy is going to go up because work has come in, but it's also going to be reduced some because work went out, because heat went out. So you would say U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. And we would say that because, this is the equation, but this is heat. Usually is heat coming in. We have heat going out. So we're going to go minus 45. And this is usually work going out, but we have work coming in. So that's actually minus 200. I know, this is kind of silly, right? Plus. All right, but that's like the convention that we use. So that's what is being demonstrated in this example. And so you could say that the change in internal energy from state 1 to 2 is going to be 155 kilojoules. And that's all we have for this example. Like I said, it was very straightforward and simple, but we want to kind of belabor it a little bit so we can think our way through and note what this sign convention is for heat and for work as it comes into and out of a control volume.